Welcome to AI Patent Watch, the podcast where we break down an exciting AI patent in each episode, what it covers, why it matters, and how it's impacting innovation. Whether you're a patent professional, an AI enthusiast, or an inventor looking for inspiration, you're in the right place. Let's dive into today's AI patent.
Welcome to the deep dive. Today, we're jumping into something pretty critical: training machine learning models inside communication networks. Specifically thinking about things like predicting resource needs in 5G, keeping everything running smoothly, top service quality. That's the name of the game, right?
Absolutely. Yeah. And when you've got these massive distributed networks, the old way of just grabbing all the data and putting it in one place for ML, it really kind of hits a wall, especially because the data from one part of the network can look, well, quite different from another.
Exactly. And that's our mission for this deep dive. We want to understand what's happening now with machine learning in networks, the state of the art, but also what are the limitations? And then crucially, how does a specific patented invention manage to get around these issues?
Right. Think of it as a way to quickly get up to speed on some key advancements for keeping networks smart.
And a big part of this conversation is going to revolve around a technique called federated learning.
Yes, FL or federated learning. It's essentially a decentralized way to do machine learning. So instead of moving all that data, you train a model across lots of different clients. It could be network nodes, devices, you name it. Each uses its own local data, and a central server kind of coordinates everything.
Okay, let's break that down a bit. So typically, the server picks some clients, sends them the current AI model. The clients train it using only their local data, and then they send back. Well,
model updates, basically.
Yeah.
Send these updates back to the server. The server then takes all these updates and aggregates them, mixes them together somehow to create a new, improved global model.
And this global model, this is what things like the NWDAF, the Network Data Analytics Function, or the ANLF use for making predictions.
Precisely. That's the idea. Use that model to predict things like network load, user movement, whatever helps optimize the network proactively.
Sounds great in principle. Distributed learning, using data right where it lives, but there's a catch, I assume.
There is, and it's a pretty significant one. Standard federated learning kind of relies on this big assumption that all the clients are training the model using data that's, well, reasonably similar.
And in a real-world network, that's probably not always true.
Often not, no. You run smack into this problem called data heterogeneity. It just means the local data sets on different clients can vary, sometimes a lot.
Why would they vary so much?
Oh, lots of reasons. Could be timing data from peak hours versus off-peak. Could be locations, think a busy city versus a quiet suburb. Could even be things like faulty sensors generating weird data, or maybe even security issues corrupting it.
Okay, so the data is different. What's the actual problem that causes for the model?
Well, the core issue is if a client's local data is too different, you might call it ill-fitting, the updates it sends back can actually hurt the global model's accuracy. It pulls the model in the wrong direction.
Right, like trying to average out numbers when some of them are completely off the scale, it skews the result.
Exactly. These conflicting updates essentially dilute the learning process, making it harder for the global model to converge on something genuinely useful and accurate for the whole network.
So how does the poor server figure out which clients are sending these unhelpful, ill-fitting updates? Can it even tell?
And that's one of the main limitations of the standard approach. It's actually really difficult for the server. Even if it has its own test data, just looking at the aggregated updates doesn't easily reveal which specific client's contribution was problematic.
Couldn't it just check how accurate the local models are?
You'd think so, but comparing local accuracies during training isn't always reliable. Accuracy can jump around a lot, especially early on, even if the data is okay. So yeah, identifying those troublesome clients is a real headache. It's something explored in prior work, like Patent CN 113-989-627A, for instance.
Okay, so that prior art highlights the problem too.
It does. And navigating this, the technical details of machine learning versus the legal patent side, it really underscores why having expertise in both is so important. For someone like you handling AI and software patents, understanding these technical nuances within the legal framework is absolutely key.
Okay, challenge established. FL is good, but data diversity in real networks is a problem. So let's get to the solution. How does this patent tackle it?
Right, so this patented method aims squarely at that heterogeneity issue. It introduces really 4 key ideas. First, the server doesn't just send the model. It also sends some metadata.
Metadata, like what?
Things like statistics about the server's own global test data, maybe the average, the spread, key features. Let's call these G data statistics. It might also send the current global model's accuracy on that test data, the G accuracy.
Okay, so clients get the model plus some context about the server's view. What next?
Second, each client then actively tries to figure out if its own local data looks statistically different from what the server described using those G data statistics.
So the client does a self-check.
Exactly. Third, the client then sends feedback about this check back to the server, along with its model update if it decides to send one. And fourth, the server uses this feedback during the aggregation step. It doesn't just blindly average everything anymore.
It's more selective based on that client feedback. Makes sense. So how does it all kick off? The initialization?
Yeah, the patent describes this initial phase. Figure 6 gives a picture. Basically, the server sets up the clients. It gets its global test data, maybe from a central store like an ADRF.
ADRF, right? The Analytical Data Repository function.
Yeah. And meanwhile, each client grabs its own local training data from wherever it stores it locally.
Okay, server has its benchmark. Clients have their training sets. Then the training starts.
Right. Into the training phase, Figure 7 helps visualize this. The server sends out the global model, those G data statistics we talked about, and the G accuracy to the selected clients. Each client then trains the model on its local data, creating its own local model, an L model. And importantly, it tests this local model on some of its own local test data to calculate its local accuracy, L accuracy.
Okay, local training, local testing. Now the crucial part, how does the client use the server's G stats and G accuracy to decide what to do? That heterogeneity check.
This is where the client-side logic happens. It compares its L data statistics to the G data statistics, and it compares its L accuracy to the G accuracy. Based on those two comparisons, it makes a decision. There are kind of three main paths.
Okay, walk me through them.
Path 1. The client sees its data stats are different from the global stats, and its local accuracy is lower than the global accuracy.
So different data, worse performance.
Right. That's a red flag. It suggests this client's data might actually harm the global model. So in this case, the client basically sits out this round. It doesn't send an update. It might even ask the server for different data if possible.
Smart. Avoids polluting the global model. What's path 2?
Path 2. Data stats are different, but the local accuracy is higher than the global accuracy.
Interesting. Different data, but it's actually working better locally.
Exactly. This suggests the client might have valuable data representing a different but important part of the network reality that the server's current test data doesn't capture well. So here, the client actually sends a request to the server asking it to consider updating its global test data, the G data.
Wow, okay. So the clients can help improve the server's own benchmark data. That's clever. And the third path?
Third path is the simplest. The client checks, and its local data statistics are not significantly different from the global ones. Things look aligned.
So it assumes its data is compatible.
Pretty much. In this case, it goes ahead, finishes training its local model, and sends a resulting model update back to the server for aggregation.
And then the server takes the updates from all the clients who followed path 3 and maybe considers the requests from path 2 clients.
That's the gist of it, yes. It aggregates the updates from the participating aligned clients. Now, there's also a variation mentioned. Figure 11 shows this possibility, where the server could actually do the heterogeneity check instead of, or maybe in addition to, the client.
How would that work?
In that case, clients would need to send their L data statistics and their L accuracy to the server. The server would then run the comparisons itself and decide whether to include that client's update.
Okay, so the check can happen at either end, but the core idea is the same.
Exactly. The core idea is you only update the global model with a client's contribution if that client's training data seems sufficiently similar statistically to the server's benchmark, potentially also factoring in whether that update is likely to improve or hurt accuracy.
And crucially, this similarity check happens just by exchanging statistics, not the raw data itself.
Precisely. That preserves data privacy, which is a huge benefit of federated learning in the first place. And this whole cycle, send model, train locally, check heterogeneity, feedback, selective aggregation can repeat over many rounds to keep refining the global model.
Okay, I think I've got the overall flow. Let's dig a bit deeper into how it works. How good are these statistical comparisons, mean, variance, etc., at actually telling if the data is similar?
Well, they're surprisingly informative, comparing things like the mean, maybe quartiles, the variance, these basic statistical descriptors. If they're wildly different between the client's local data and the server's global data, it's a very strong hint that the underlying distributions are just not the same. It might not capture every nuance, but significant differences in stats usually point to significant differences in the data itself.
And what about that accuracy check, the L accuracy versus G accuracy? Why is that needed if the stats look okay?
That's a really vital sort of safety net. Sometimes the basic stats might look superficially similar, but maybe the relationship between features is totally different, or there's some subtle issue. If the client trains a model locally and gets much worse accuracy than the global model, even with similar stats, that's still a warning sign.
I see. So stats say maybe okay, but performance says nope.
Right. Or conversely, like in path 2 we discussed, if the stats are different but the local accuracy is better, that accuracy check is the signal that says, hey, this different data might actually be really valuable. It triggers that potential update to the server's view of the world.
So it's this two-pronged check, data shape and model performance.
Exactly. And this whole feedback loop where clients report back their findings is what empowers the system, whether it's the client deciding locally or the server deciding centrally to be intelligent about aggregation. It filters out the noise, the potentially harmful updates.
And you mentioned potentially updating the server's test data, the G data. How does that help?
That's key for generalization. If a client consistently performs well with data that looks different, incorporating characteristics of that data into the server's benchmark helps the global model learn to perform well across a wider range of network conditions. It stops the model from becoming too specialized to just the initial G data profile. And the invention also explicitly mentioned the possibility of refreshing or updating the training data on the client or the test data based on these checks too.
It's quite a sophisticated process dealing with these statistical comparisons, accuracy thresholds, the feedback mechanisms. It really highlights that getting this right, especially when you're thinking about protecting these ideas with patents, needs a deep understanding of both the AI tech and the patent law side of things. Experts like yourself, Bastian Best, working as a European patent attorney in this AI and software space, are essential for navigating that intersection.
Well, it certainly keeps things interesting. You need to understand what's technically feasible and novel, and also how to define and protect that innovation legally.
So bringing this back to the network, can you give some concrete examples in, say, a 5G system where this would be implemented?
Sure. The patent itself gives a few examples, looking at figures 8, 9, 10. You can imagine the FL server being part of an NWDAF, specifically one with a model training function in MTLF. The clients could then be other NWDFs, also with MTLFs, distributed geographically. The final model might be used by an NWDF analytics function, an ANLF.
Okay, so NWDAF to NWDF learning.
Right. Or another scenario, maybe an application running the core network, an application function or AF, acts as the server and the clients. They could be applications running directly on user devices, the UEs.
Training across phones, potentially.
Yeah.
Very distributed. And the payoff for all this complexity, what's the benefit of getting more accurate models this way?
The payoff is better network performance and better user experience. More accurate predictions feed into better decisions by all sorts of network functions, the PCF for policy, the UPF for data traffic, SMF for sessions, AMF for mobility, those AFs we mentioned.
So, give me an example.
Okay, think about predicting where a user is going to move next mobility prediction. If the model is more accurate, thanks to handling data heterogeneity better, the network can prepare resources in the right next cell more effectively. This avoids things like dropped connections or sudden buffering during video calls when someone moves. Fewer inaccurate predictions means less wasted resources and smoother service.
Got it. Better predictions lead to smarter resource allocation, preventing problems before they happen.
Exactly. And the patent also notes, the underlying system to run all this, figure 13, shows a generic idea. It's a data processing system with the usual components. Communication interfaces to talk to the network, memory for the data and models, and a processor to run the training, the statistics, the comparisons, all that logic.
Okay, so let's wrap this up. To summarize this deep dive, what we've seen is a patented approach that really advances federated learning for these complex communication networks. It directly confronts that data heterogeneity problem.
Right. It does that by having this clever exchange of metadata, allowing clients or the server to check for data similarity using statistics, factoring in actual model performance via accuracy checks, and using that feedback to make the aggregation process much smarter and more selective.
The goal being more accurate, more robust ML models trained right across the network.
Precisely. And that's becoming increasingly vital as networks like 5G get more complex and we rely on them for more critical applications. Better models mean better service quality.
It really has been fascinating. It leaves you wondering, doesn't it? Looking ahead, with networks only getting more complex, more data heavy, how crucial will these kinds of smart adaptive training methods become just to keep things running seamlessly for all of us? And maybe what other areas, completely outside of network management, could really benefit from this kind of robust federated learning that can handle diverse data? Definitely food for thought. Thanks for joining us on The Deep Dive.
And that's a wrap for this episode of AI Patent Watch. If you found this helpful, please take a moment to leave a 5-star rating and subscribe so you don't miss future episodes. This podcast is curated by Bastian Best, a European patent attorney specializing in AI patents. To learn more about the exciting intersection of patents and AI, sign up for his mailing list for exclusive insights. Link in the show notes. And if you're already working on the next big AI innovation, now's the time to secure your own patent. Reach out to Bastian on LinkedIn or the podcast website to turn your ideas into assets. Thanks for listening and stay tuned for the next episode of AI Patent Watch.